Hey, how's it going, everybody? So what we're going to do today is we're going to work a full RLC series circuit. So in the previous video, we focused on impedance and voltage total only. Okay, so we were just mainly looking at the triangles. And I would like to stress that the power triangle is the same thing. If you look at your formula sheet, you're going to see that your power triangle, your voltage triangle, and your impedance triangle are all set up identically. Okay, so today we're going to work the entire circuit. Okay, so let's think about what some of our rules are for series circuit, and there's one very important one. All right, and that is that current stays the same in a series circuit. If you know that, once you find one of these currents, you have the current everywhere. And then once you have that, pretty much from there, it's just going to be Ohm's Law. So I know the biggest struggle this semester has been, where do you start? Because once you get started and you get on that roll, these circuits are very easy. Okay? It's just the getting started part that's tough. So let's look and see what we have with this circuit. So in this circuit, I have one resistor, one inductor, and one capacitor. Now I want to stress, we're working with just one component of each. But if you had multiple components, all you have to do is group them exactly how we did in the previous video. And then everything else is worked the same way. I always said if you can work it with one component of each, you can work it with 3 or 4 components of each. Alright, so this one I made a little bit shorter of a circuit because we have some weird missing values here. And a lot of your tests will be set up very similar to this. So you'll have some weird missing values just like the last one that we took. So let's look and see what we have. So I told you that we have a resistor, inductor, and capacitor. We know that the circuit is 60 hertz. Okay, so that's my frequency. So let's look at our individual columns here. So I'm going to look at the totals column first. In my totals column, all I have is the information that I have 220 volts for my source. Looking at the resistors column here, so VR, IR, R, and P, all I know is the resistors value, which is 200 ohms. And then looking at the inductors column, I know the inductors value, and I know the voltage drop across that inductor, which is 392 volts. Okay? Looking at the capacitor, I know the capacitor's value. But the only other thing I know is that it's 300 ohms of capacitive reactance. So I just want to give you guys just a little bit of a hint here. These L and C values are only good for calculating one thing, and that's going to be XL or XC. Okay? So if I give you an inductor or a capacitor value, and remember, I will always give you guys frequency. That's where you want to start. You want to start with the fact that you know an inductor value, you know a capacitor value, so solve for XL and XC. So that's really the big point where we're going to get started in this circuit. Okay, so that's where we're going to start. So looking here, I already have XC. So I'm good there. So the next thing I want to find is going to be XL. Because I know L and I know my frequency. Okay? Make a mental note of that. Put it in your notes. If you have an inductor or capacitor value, that's the Henry value or the Farad value. And you have frequency, find XL or XC. Always start there if you have any of that information. Alright, so next what we're going to do is we're going to use our formula to find XL. So in order to find XL, I'm going to do the formula. XL is equal to 2 times pi times frequency times the value of that inductor. All right, so once I have that, once I have XL, I will have two things in this column. So that means that from there, I can just go to Ohm's Law, okay? So remember the shortcut. Anytime I have 60 hertz, 2 times pi times 60 is going to be 377. So essentially what I have here is 377 times the value of my inductor, which is 1.06. So doing 377 times 1.06 will give me my inductive reactance. So remember, inductive reactance is the amount that I'm limiting current through this inductor. Everything in this column going across here is going to be measured in ohms. So in the calculator, do 377 times 1.06, and that's going to give me essentially 400 ohms. So if you're following along, we're going to go ahead and just round that to 400 ohms. So XL is 400 ohms. So now, once I've got that, where do I go? Remember, I have to have at least two known values in order to use Ohm's Law. So do I have two values here? Nope. Do I have two values here? Nope. Do I have two values here? Yes. Remember, we can ignore the L and C. They're not good for anything but to figure out these two things. But across the inductor, I know that I have 392 volts and I have 400 ohms of inductive reactance. So if I have a voltage value and I have an ohm value, I can now find current. And once I have current through that inductor, if I know how much current is flowing through this inductor here, that means I know how much current is flowing everywhere, because this is a series circuit and current stays the same. So in order to find current, I'm just going to use Ohm's Law, okay? So I'm just going to use Ohm's Law. So that is going to be current through the inductor. So IL is equal to VL divided by XL. Because it's volts divided by ohms to give me current. And my ohm value in this case is XL. So I'm going to have 392 divided by 400, and that'll give me the current through that inductor, which will also give me the current everywhere. So 392 divided by 400, that is going to give me 0.98 amps. So 0.98 amps. So remember, once I have that current, that's the current everywhere. So IC is going to be 0.98 amps. IR is going to be 0.98 amps. And I total is also going to be 0.98 amps. Okay? So now, from here, smooth sailing. From here, it's just going to be Ohm's Law. So now I can start in each column and then work all of my other values. And some of you may have noticed that power factor and angle theta is missing. That was on purpose because I ran out of room trying to work with a smaller board here than in the classroom. But we will go back and add that at the end. I just wanted to make sure I had room up here to write out formulas when needed. All right, so let's start in our totals column. All right. So let's look at what we have in the totals column. I have voltage and I have amps. So that means that I can find Z, which is impedance, which is an ohm value, and I can also find VA, which is the apparent power. So remember, everything in the Z column here, Z, R, XL, and XC, are all the same. They're all treated the same when it comes to Ohm's Law. Okay? So, in order to get Z, which is ohms, I'm going to have Z is equal to voltage, which is 220, divided by current, which is 0.98. So 220 divided by 0.98 will give me my impedance, which is the overall current limiting property here in the circuit. And we'll go back and check ourselves here in just a few. So 220 divided by 0.98, that's going to give me 224 0.49 ohms. Alright, so I'll give y'all just a second. If you want to pause it, make sure you get these values, okay? Alright, so now that I have impedance, remember VA and everything across here is part of that power triangle. So that means that as far as Ohm's Law goes, they're all the same. So VA is going to be volts times current. P is volts times current. VARs is volts times current. So all of these are treated the same way as far as Ohm's Law goes. So in order to find VA, it's going to be VA is equal to voltage total times current total. So that gives me 220 times 0.98. So 220 times 0.98. And what does that give everybody? You should get 215.6. Okay? So 215.6. Alright, so now let's move over here to the resistors column. Alright, so now that I'm in the resistors column, let's look at what I have. I have current and I have resistance. So that means I can find voltage. Everybody should know that Ohm's Law formula. It is VR, voltage across the resistor, is equal to I times R. So IR times R. So I have 0.98 times 200. So 0.98 times 200, and that should give you 196 volts. Okay? Easy enough. See, it's not that bad as long as you know how to get started. Once you get started, it's pretty smooth sailing from there. Okay? So, now, we just got to find power. We know that power is pi, or P equals I times V. So P is equal to volts times current. And it's going to be the same thing for VARs. Okay? So 196 times 0.98, and that's going to give me 192.08. Okay? So now, moving to the inductors column, I have everything that I need except for VARs. So remember, VARs is a part of the power triangle, okay? So if it's a part of the power triangle, I treat everything in this column here the same. So VARs L is equal to voltage times current, just like I did with power. So 392 times 0.98. So 392 times 0.98. That gives me 384.16. All right, so now moving to the capacitors column. I have two missing values here. I have the voltage and the VARs to find. So with the voltage, I have current and I have my ohms, the capacitive reactance. So in order to get voltage, VC, is just your standard Ohms Law. VC is equal to IC times XC. So that's going to be 0.98 times 300. So 0.98 times 300 is going to give me 294 volts. Okay? Now, we need to find VARs C. Alright, so it's a part of the power triangle, so guess what? It's volts times current. So 294 times 0.98 is going to give me VARs C. So 294 times 0.98, that's going to give me 288.12. Now, a couple of things before we check ourselves and then we go through power factor and angle theta. As mentioned in the last video, or actually I think it may have, yeah, it was the last video, I said that it is very, it's not uncommon to have a voltage across your inductor that well exceeds voltage source. And you can also have that across the capacitor, because think about what's happening. All right, yes, this is creating a pressure difference. It's limiting current based on that resistor's properties. But here, this is CMF, essentially. Okay, so that's why you can sometimes see that inductor voltage get so high. Because when we have that current and it flows through this coil, we're going to induce that magnetic field and induce that voltage, which has that CMF. Okay, so again, it is not abnormal at all for VL to be higher than VT. If you see that, it's okay as long as everything checks out. So that's what we're going to do really quick before we find power factor and angle theta. So let's do some triangles to see if all of this checks out. And this will be a good review for your triangles. All right, so remember, the voltage triangle is essentially going to be voltage total, resistance, and then right here, not resistance, VR, and then essentially this side, remember we plotted that on the graph in the RLC basics, but essentially this side here is going to be VL minus VC. Because remember, they're 180 degrees apart, so this side of the triangle is the difference between VL and VC. So, what we're going to do, let me
back.
All right, so what we're going to do is we're going to set this up into a triangle. All right, so what we're going to end up with is VT is equal to the square root of VR squared plus parentheses VL minus VC squared. Okay, so that's what we're essentially going to have when we're checking our voltage. Okay, so let's check it. So let's erase what's inside here and write our actual values in. So VR is 196 squared plus parentheses VL, which is 392, minus VC, which is 294, and then squared. So let's plug this in and see if we indeed have 220 volts. So we're going to do 196 squared plus parentheses 392 minus 294 close parentheses squared, hit your equals button, and then square root it. And we end up with 219 and some change. Okay? So we just checked out. Okay? So we know that our voltage values are correct because it equals 220. Okay? So again, in the calculator, you're going to key in 196 squared plus parentheses 392 minus 294 close parentheses squared, hit equals, take the square root, and you should have 220. Now, for those of you that have the more advanced calculators, that's more advanced than the old TI-30XA here, you can actually put it in exactly how it looks. So, key your square root button, the number squared plus parentheses, this minus this, close parentheses squared, hit equals, and you're good. Okay? Just got to work a little bit harder when you have the more simple calculator. All right, so we know current. Current doesn't have a triangle. So let's go to the impedance triangle and just make sure that that checks out. So on my impedance triangle, it is set up the exact same way as the voltage triangle. So I have Z, R, XL minus XC. Okay? So, to translate that into a formula, I would have Z is equal to the square root of R squared, so that's 200 squared, plus parentheses 400 minus 300 squared, and that should give us our answer. Now, if you know 400 minus 300's 100s, you can go ahead and just do that if you want. But just for clarification purposes, so nobody gets confused, I'm writing the whole thing out. Okay? So I have 200 squared plus parentheses 400 minus 300 close parentheses squared, hit equals, take the square root, and I have basically 224. Okay, a little bit of rounding error maybe, but it's close enough. We're within that 5% range. Okay, all right. So I know impedance checked out. So you can do the same thing with apparent power. So we won't go through it, but essentially it'll be set up the same way. So your power triangle is just going to be VA, power, and then you're going to have VARs L minus VARs C here. Okay? So that translates to VA is equal to P squared plus parentheses VARs L minus VARs C squared. Okay? So one thing I noticed, and I will send this out in an email, is the formula sheets that were copied from one of the books was actually wrong. So if you guys would please write this formula in your notes, because this formula is not correct. Okay? This formula is not correct in the formula sheet. Okay? All right. So once you do that, you should get 215.6. All right, so now let's do power factor and angle theta, and then we will be done. Okay? So power factor and angle theta. So remember, power factor and angle theta can be any resistive component divided by its total. Okay? Because basically what we're looking at is our triangles here, and we're finding this angle here, angle theta. And we're finding that percentage, that ratio, and then we're finding what this angle actually is. Okay? So, let's start out, and let's just do VR over VT. So VR would go here, VT is here. So when I do VR over VT, ultimately that's going to be in reference to angle theta adjacent over hypotenuse. Okay? So adjacent over hypotenuse. So that is the cosine function. So first, let's get our percentage. So I'm going to do 196 divided by 220, hit equals, and then we're going to times that by 100 to give us a percentage. So what you should get is 89%. Not a bad circuit, actually. Okay? If the capacitor wasn't in there, it would be way worse than that. Probably in the 30-40% range. But since we added that capacitor, we did some power factor correction there. So we improved our power factor. So what that means is you can pretty much draw the conclusion that angle theta is going to be small. If your percentage is high, your angle is small, and then vice versa. So let's do 196 divided by 220 again. And with that decimal in your calculator, just a 0.89, second in cosine, and that's going to give me 27 degrees. Okay? So that's a pretty small angle as compared to 90. So looks pretty good. All right? So we can do a couple other things to check. We can also do R over Z, and we can do P over VA. So remember, if you do have multiple VRs, multiple Rs, and multiple Ps, you always want to add it all up. So add up all your VRs if you have multiple, and then divide it by VT, and so forth. Okay? So let's just try it out, and let's do 200 divided by 224.49. It equals, and that gives us 89% and 27 degrees. We can do P over VA, which is the formula we normally use, 192.08 divided by 215.6 equals, and I get 89. Okay? So I know that was a lot, but you have this video. You can watch this multiple times. You can pause it, whatever you need to do. I really encourage you guys to draw these circuits out. Don't just watch the video. Draw the circuits out and work along with me. Okay? Alright, so if y'all have any questions, please feel free to reach out. So remember that worksheet will follow. I'm probably going to give y'all tonight to watch this video, and I'm going to post a worksheet. And I may go ahead and post a study guide also. And I will have answers for that study guide, so that way y'all can work the study guide and so forth. Just to try to boost some grades on some of these tests. Give y'all some practice problems. Okay? So if you have any questions, please let me know. Remember, okay? Remember the first worksheet that is already on Blackboard is going to be due on Wednesday. And then the next worksheet and the test will be due by Friday. And that's end of day, so 11:59 p.m. both days. Okay? So if y'all have any questions, please let me know. And y'all have a good day. Stay safe. Okay?